next lecture. So this is week number 3, and then next week we have a week off. So last week we talked about travel time, and we covered part of the travel estimation. And then today, this week we're going to talk about travel time estimation, follow on from last week, and then we talk about incident management. So do you have any question for last week? Any question about the assignments? Have anybody tried assignments?
Yes, but the graph is so weird.
Okay, so
I cannot find the piece of the I cannot find the model.
Okay, so we can talk about it during the tutorials about how some of the questions about the assignment, which is good. I've also uploaded new data into the Blackboard. Any other questions about the lectures or about my lecture? Do you want me to? Am I speaking too fast, too slow? Is the pace? You were in my class last year? But you enjoyed it so much you come twice. Okay. Any comments about my class? You want too fast, too slow? You want more notes? You want too little notes? Anything I should change? No? Okay. So we'll do a recap of last week. So we talked about travel time information and what type of information that we want. Right? And we talk about, we want information that's accurate. So there's no point having information that's not accurate because then it's not useful. Accurate, it has to be reliable. So that means that you can go back and then there's a source that you are confident that you can get good information. It has to be timely. You don't want information to come to you which is too late for your travel. Relevant to what you're doing, it should be easy to understand. That's why we talk about travel time, which is much easier than the length of congestion or the speed, right? Because for travel time, you understand that it's going to take me a certain number of minutes to get to the destination. Also, information is useful because it's allowed us to make informed decision about what we want to do, whether we want to take a train, whether to take a bus, whether we should be taking route A, route B, not traveling, things like that. So that's important. Another very important point about information, especially for travel time, is that travel time we talk about, which is very easy to measure. Because every time when we travel, we time when we start, we time when we finish. So that's our travel time. But the travel time, you can only measure the travel time after you finish your travel, right? So after a person finishes the travel, that time is past. So if I want to travel now, I need to know what my travel time will be. So therefore, we need to do some kind of prediction. Okay. Historical data. From the historical data, of course, we can measure what my travel time was when I left at 8 o'clock yesterday morning. So that's possible. But today, if I want to leave now, I would like to know what my travel time will be. So I do not know yet. Nobody could tell me. So we need to do some prediction. That's why this is part of the work. Okay. We also mentioned about 2 different travel time. One is instantaneous travel time. Because a link is very long, so for example, we can get more travel time information from short links. Because how can I say? If you want to go from here to the end of the new territory, to the border between Hong Kong and China, not many people is going to go the whole way through. Okay, so if you want to find the travel time, and if you want to use people who move from here to the border, not many people will do that. So the sample that you're going to get is very small. Okay. So what we could do is that we could take people from here, let's say, to 2 stations from here, and then from 2 stations from here to the north. So we split that trip. So let's think about this. For example, if we are here, and this could be the border. So not everybody goes from here to the border, right? But there are lots of people traveling back and forth. So if we know travel time here, travel time here, travel time here, we have a bigger sample. So bigger sample means it's more representative. Okay. So if you have sample of 50 at each of these, it's much better than when you have only 3 or 4 people, right? So the variance is very large, so it's not very good. So partly because of a sample size, we can break down this long corridor travel time into small sections. So there are 2 ways, in general, how you can work out the travel time. So if you know the travel time for each section, we can sum the travel time for each section. So that gives you the corridor travel time. And this is what we call instantaneous travel time. So that's the travel time for that instance, for that time. So you sum them all up. So it's very quick, it's very simple. There are some drawbacks of this. So that it's assuming that the condition doesn't change. So that means that it doesn't matter when you're traveling as you move along, the condition will be what you're going to experience right now, right? Right at the time when you sum them up. So quite a lot of time, that's okay. But there's some period that's not good. I will show you. So when the traffic flow conditions around like those places, it's quite okay. Not quite sure about this one, but at least for the low flow situation, it doesn't change so much. That's okay. So instantaneous travel time and another method, time slice, you will find very, very little difference or not. So it does. So the quick and simple method is okay. So during when the peak is increasing or decrease, when the congestion is increasing or decreasing, another method is what we call the time slice method. So instantaneous is basically the summation of all your link travel time. And instantaneous, time slice method is that you work out the travel time for each link because from historical data, and then you look at the travel time what the travel time will be once you get to that point. Okay, so that's how the instantaneous travel time is calculated. So, anybody wants me to explain what instantaneous travel time? Do you understand? Do you know how to get it to work? Yes? No? You all are very clear? So last week, I gave this slide. It talks about link travel time, right? And if you have gone through the notes, you will understand this. But some of you may find it difficult to follow. Okay, so if you don't understand, you have to let me know. So it talks about here you have it talks about the travel time for the first link is 5 minutes, the second is 12 minutes, and so forth. So basically, you don't sum the travel time up like that, but you would look at, because it takes from here to here 5 minutes, and then at 8 or 5 you check the time what that's going to be, and you do some it's actually quite simple, but if you don't, it may be a little bit difficult to follow. So I use this slide already. So it's this period where the time slice method is much better. So I'll I got the slides ordered not very right. So imagine that in your this is very similar to your assignment, right? So at let's say every in this example I use every 5 minutes. So you have a link A, B, C, and D. So at 8 o'clock from the historical data, you calculate that these are the travel times. So this is 6 minutes, 14 minutes, 24 seconds, 8 minutes and 38 seconds, 4 minutes and 19 seconds, right? At 8 o'clock in the past, let's say yesterday, 8 o'clock. This is the information that you have for all the links at 8 o'clock. So if you use instantaneous travel times, you sum all the links up. So basically you just put this one plus this one plus this one plus this one, basically give it this time. Okay. So this is what instantaneous travel time is. So same thing for 8:05. This one plus this one plus this one plus this one plus this one, it gives you the travel time. This is instantaneous travel time. So in this example, what you can see is that for link A, it's just constant, so it's just, there's no congestion. It doesn't matter what time it is, it's still just 6 minutes. Link B, link C, and link D, you can see that the travel time as you move along, it goes from 14 to 21, and then it goes, after 21, it can't peak, and then it drops. Okay. Link C is the same, it has similar pattern, it just goes up, peak at about 8:30, and then it slows down. So it goes up quite quickly, and then it goes down. Okay, so that was the travel time pattern that we get. So what it means is that at 8 o'clock, as you travel 6 minutes, you're hitting the congestion. Okay, but if you come a little bit later, the congestion is decreasing because when you get to link D, you're at the end of the trip, at the end of the congestion, right? the peak period. So if you look at the instantaneous time, if you sum them all up, it's exactly like this profile. So it goes, it increases to about 8:30, and then after 8:30, it decreases a lot as well. So this is what you do when you get an instantaneous travel time. So if I put it into a graph, so this is link A, link B, link C, link D. So if you sum them all up, this is what you get, exactly the same as the profile that you're going to experience. Okay, so this is instantaneous travel time. So we are interested in the other method as well, because remember in the previous graph we thought if the condition is not stable or not the same, because remember if you start at 8 o'clock, there's congestion along the way, right? So it's not going to be the same. Likewise, if you are traveling around this time, you can see by the time you get to the next link, the congestion is actually improving. So you are hitting the lower part of the congestion period, right? So in this situation, the time slice method is much better, right? So I've explained to you, this is the same diagram, same. These values are the same. Okay, so I'm just going through the exercise so that you understand what time slice is. So at 8 o'clock, link A is 6 minutes. So what time will you get to link A? What time will you get to the end of link A? So if you start at o'clock, link A is 6 minutes. So what time would you get to the beginning of link B? 8 o'clock, takes 6 minutes. How long do you get to the start here? No? So it's 8 o'clock. The travel time it takes is 6 minutes. How 6 minutes? So how long will it take to get? At what time would you reach the end here? 8:06. Okay. So you get to this point 8:06, right? So at 8:06, if you look at these are historical data, right? Because you know the past. So 8:06, perhaps we should look at maybe this one. This is because this is 8:05 to 8:10, right? Around this time. So we need to use this link B because at 8:06, this is what you will experience for link B, correct? So we add these two together is 21:54, right? 8:21:54. So by the time you get to this point, what you should be experiencing is here, correct? It's 20. So it's this point for link C. And then you get to link C, so this is 21, is it correct? 21 plus this one is about 40-ish, right? A little bit over 8:40. You reach link D at about 8:40. So 6, 15, 18 because it's about 1 minute, so it is about 40. So 8:40 is a little bit. Okay. So we look at this time. This is you get to link starting from link D at this time. So then the link time is here, 16:36. Okay. So this is how you work out the time slice diagram. Right. So when you do it this way, you find that the link time slice travel time is like this. Okay. The same thing for other time slice as well. So for example, in this, let's say 8:20, right? 8:20 is 8:26. 8:26 probably around here, so you need to add this one plus this one, so that's 27 minutes. So it's about here. Then you need to take another one here. So you take this one, and this one, like that. Okay. Is it clear? Okay. So if we look at the graph, so remember we found the red line. This is the instantaneous travel time. With the red line, this red line comes from this method here, like that. You can see that there's a difference between the two methods in this example, right? The travel time is a difference. So what happens is that if you sum them all up in the beginning, because the congestion is increasing, so the actual time you experience is something here, closer to this one, right? And then if you leave it at 10, the time that you're going to experience is actually less than what they're predicting. You can see, because over here you're experiencing this part already. When you get to the later part of the tree, right? You're in the downside. So you can see that the two methods for such a conditions, there's a difference. Okay. So let me go back and use another example. So if the link, for example, if you copy this value, consistently down this way, right? So let's say 8:00, 8:05, 8:10, rather, it's always 6 minutes, 14 minutes, 8 minutes, 4 minutes. So 6, 14, 8, 4, like that. Okay. So then you'll find that no matter whether you sum this way, it's the instantaneous, or the time slice method is exactly the same, right? Because nothing changed. Okay, because 6 minutes and then you say, then you check the next value. So it doesn't matter which way you check; it's exactly the same value, right? So if you transpose that, maybe next year you modify the slice method. Remind me of that. So if the condition doesn't change, so it doesn't matter which method that you use, they are very similar results. So both are okay. But when the conditions are changing, then you find the results. Okay? So I hope you understand this point. Yeah. Okay. So it's quite simple, but once you understand it, it's quite easy. Any question? Because I think last year some of your classmates were asking me about this. Some people find it hard to understand, so that's why I changed a little bit of this way. Probably better this way. Probably better than last year. Okay, good. He was in my class last year. Okay. Travel time prediction. So we talk about why we want to predict travel time, because we cannot measure it, right? So that's why we have to predict. From history we can know, but if you want to know what our travel time will be, we have to do some kind of prediction. So one of the simplest method in terms of predicting, in fact we do that all the time, is that we rely on our history. Okay? So it's a bit like every morning, how long that will it take to get from your home to PolyU? You will, especially if you are taking a bus, because the congestion is different, you never know what will be. But roughly you know, because you have been doing it every day, right? So every day you're doing it, you have some idea. Okay, it may be 20 minutes to 25 minutes or something. So that's how you planned your trip. But where do you get this information from? These are from your experience, right? So these are the historical information that you have. So there are many methods that we could do, and most of the methods rely on some kind of history. So from the history, what can it tell us about today? You know? So in the past, we know that that's the situation, and then what is it going to be for today? So there are some techniques that you could use. So there are some time series analysis. So I will not go into detail, but if you're interested, you can read about ARIMA, autoregressive integrated moving average. So that's a kind of a approach that you could use on to do the prediction. So basically what it does is that it looks at the history and it looks at the current situation, and then it predicts. It says, okay, well, based on the past train, the train of the travel time and today, I think the travel time is going to be such. Okay. Another one is on the sand glass method. So this is more a kind of a theoretical base. What it does is that it says, okay, well, today I know the traffic congestion or number of cars on the road is this much, and I know the capacity at maybe the Cross Harbour Bay tunnel is this much. So from there, I can work out, how long it would take for these vehicles to clear. Okay, so that's more on that aspect. So you know the demand, you know the capacity, so you work it out. Okay, that way. So this is what the sand glass method. The reason why it's called sand glass method is so I think since we are very near here, it's great example. So if this is the Cross Harbour Bay, Cross Harbour Tunnel. And this is a perfect example. So you can see that we know how many people are coming in to cross the tunnel, and you know how many people can cross the tunnel. Okay, so if we know how many people are coming towards the tunnel, how long will it take the people who are here to get to this point here, right? Because so if you know, let's say there are 10,000, and then this can only take I don't know, 3,000 per hour. This is 10,000. So it take quite some time for them to clear, right? To get there. So you can work it out. There is a very simple technique. So oops. Stained glass method is like that, right? You know the hourglass, the old-fashioned glass, like that. So it's like that kind of technique. Okay. So you can see this doesn't really rely on historical method. It doesn't really look at past history. But of course, there's a lot of assumptions here. Okay? The assumptions here is that you know the capacity, you know the demand. Okay? So if you know the demand, you know if you know the demand, you know the capacity, that's okay. So another method is pattern matching. So I'm going to talk about two approach you can use. So we talk about pattern matching in the sense that you know, just like you know, ahead we know that from the past history, okay, this is what we experienced, and then from there, I think today's travel time is going to be this. This is for you to come to Poly. But if you want to go to another place that you have, maybe you want to go to a movie somewhere, but you have done it a couple of times before. So again, you look from your past. Okay, well, in the past I've been there a few times. This was the pattern, and then that's what I think you take me today. So again, you look for the pattern in the past, and then you predict forward. So this is a non-artificial neural network or non-machine learning techniques. Okay, so we have the detector data. You look at the trap, and then this is today's pattern. And then you do a pattern matching. So you match in the history what you have today. You see what's the closest pattern that you can see, and then sorry. This is the detector that you get today, sorry. You get today's pattern, and this is the historical data of the patterns that you have. And you match them. So a couple of things that you have matched before, and then you look at the prediction. Okay, so the approach is quite straightforward. These are historical data which you have collected over over a year, 2 years. Okay. And this is what you have today. Okay. So you match what the pattern here with the history, and then you select some of the similar ones, and then you do the prediction. So in pattern matching, so you have traffic patterns. What you try to do is you look for traffic patterns similar to today. Okay. And then from this similar pattern of the history, you think that, okay, the travel time is likely going to be similar. So then you use that as a projection. So you need historical data to do that. So just look at one example here. Assuming that we want to use speed as a measure. So each of this section here, you can have a speed value from history. So you have the sensors that measure the speed. This is time. This is your space, right? Time-space diagram. So each time interval, let's say just like the example that we had, is 8:05, 8:10, and so forth. Okay. So each section you have a value, and you can either use the exact value, or you can make it like a speed contour map. So you can turn it like a speed contour map like that. Now, so this is what you mentioned today. So let's say from 7 o'clock until 8 o'clock here, this is the speed that you get. This is the speed contour that you have. And in the historical database, well, because you're collecting every day, so you have the 24 hours of this kind of picture, and for many days on the historical database. So you have a day 1, like that. You have a day 2, and then you can, so this is like your first day, you try to match this pattern with the contour that you have already seen. So you want to see which one of these side is closest to what you have. Right? So this is what you measure today, and then you look for the history to see which one, where is it closest. And then you do the same thing for day 2, day 3, day 4, and so forth. So you search for the, sorry. So you repeat the search, okay, every day you search. So you search for those days that you have pattern closest to today. Okay? So let's say from 7 to 8. So after you have selected end best pattern, then what you can do is that because these are historical, these are the, let's say this is 10, right? So these are from the 10 closest match that you have from the history. But because it's historical, you know the whole day for that day, right? So you know the travel time from that point onwards. So you have now 10 different travel times that you want to use. So you can doing some filtering for outliers, and after that, that becomes your predicted. So basically, you're using historical information to match what's closest today, and then to predict forward. Okay. So this is one of the ways you can do, which is not machine learning based, right? Do you want me to go back? Okay. Okay. So I'm going to spend the next 15 minutes or so talk about artificial neural network or machine learning type of technique. So before that, it's really about just finding a present pattern, and then you match that windows. So you just use historical data. But nowadays, people talk about machine learning, neural network, and so forth. So they are, and it's quite well recognized area now, and it's very popular. Right? So I'm just going to talk about artificial neural network, so which has been around for a very long time. So this is a little bit different from. It's just a subset of the deep learning and machine learning. So artificial neural network gets its name from, it's inspired from how our brains work. Okay, so this is how they like to write some mathematical formulas or model to mimic the way how our brain functions, how we recognize things. Right? So it's trying to mimic the learning process of the brain to develop algorithms that can be used to model complex patterns. So that's why it's called artificial neural network. So neural is just like neurons in our brain. So in the neural network, you have to train the model. You give them some training data sets to learn. Then after that, you have some testing data sets to test whether it has learned well or not. So the good thing about neural network is that it doesn't need to have any knowledge of what you want it to learn. Okay, so there's no knowledge of that at all. And then purely from the data, it will pick up the characteristics of what the data says. So in the neural network, you have your input layer, your hidden layer, and your output layer. So the input layer would be the data that you want to feed into the model. The output layer would be the answer that you want. Okay. So this is in between these, the neurons here, they are connected to, so from input layers to hidden layer, they're all interconnected like that. For each of these connections, there is a weight. Okay, the weight. Let me see what's there. So when you through this input, through these trainings, so what you're changing is actually the weight of these connections. Okay. So the one that has more relevance, the weights would be higher. The ones who have less relevance, you will have lesser weights. So that's how it works. So in terms of a neural network, you train the neural network with training data. After you train the neural network, you have a separate test set to test whether the network is working. And the neural network performance depends on the quality of your data. So a simple example would be how we learned about different things. And one other example I could think of is that, when a child is born, they have no idea about anything. So if you teach a child to recognize fruits, for example, right? So he says, okay, well, you hold an apple and you teach, this is an apple. Okay. So obviously they have never seen an apple first time before, so that's an apple. And if every day you bring an apple and show them apples, so they start to recognize that, okay, this shape, this size, this color, and so forth, that's an apple. Okay, so gradually they learned from that, because through this training, so it's like training. So you give them apple, and then soon they recognize that's apple. Right? And then if you give them an orange, probably they says, oh, they do not know because they've never seen one before, right? So this is how we learn. So we haven't told them anything, the brain, that, okay, it's apple, we program nothing, we just say, that's the shape, they start to recognize that's an apple. And of course, every day if you give an apple that's red color, for example, they recognize there's something red, that shape, that size, that's an apple. So what do you think will happen if you give them a green thing, green apple? Do you think they will know that it's an apple? Maybe not. Or if you give them a yellow apple, would you think that they know it's an apple, right? So the reason why I mentioned about the different types of apple is the quality of the data for your training. Okay? So if you give them a very rich data set, they learn better, right? So if you just give them apple, red, so then you give them green apples, sometimes they may guess, right? Sometimes they may guess incorrectly. But the quality of the data is important. So some big apples, small apples, but they're all apple. If you train them well, they will understand that's an apple. Okay? So neural network is a little bit like that. So your training data quality is also very important. Okay. So train data set. So if your train data set is a bit like that. So obviously they start to recognize that that's an apple. And then we have a problem because the green one is not quite an apple. So if you have a very rich data sets like that, so that they start to recognize the different types of apple. Okay. So if you look at just apple itself, there are lots of variety. Okay. So if we train them well, then they should be able to recognize apple very well. Then there's issues about the one on the right. Is it an apple? Is it not an apple? So when does it still being recognized as an apple? So how is that relevant to transport? Is that sometimes probably in the data, in the assignment data, you find that some days there's no data, or missing data, or the data may be a little bit, may have some error. So it's a bit like that. It's not really a perfect data that you feed in. You also want it to be able to learn sufficient enough to think that that's actually an apple too, right? To be able to pick that up. So that's the relevance, not just a picture, but in terms of transport, that you don't get perfect data every day, every minute. So sometimes you have missing data, sometimes you have a noisy data, and you want them to be able to recognize that. Okay, so you need to test that. And hopefully they know an orange is not an apple. Okay, so this is very pictorial, and later after these slides I will show you some. I will talk more about the advantages and disadvantages in more detail. So the good thing about neural network you find is that it has the ability to perform for incomplete data. Just like the Apple I mentioned to you. Or in terms of data, when you have a bit of noisy data, it still works quite well, depending on how noisy it is. So it's able to model complex non-linear relationship. So if it's just it's just a very simple relationship, you can write an equation. Say y equals x plus b, for example. That's a very simple linear relationship. But sometimes things are not so easy as a simple straight line, right? So if it's more complicated, you don't have a perfect way to describe the shape, then a neural network can be very useful. Now, the disadvantage of neural network is that it's always looked upon as a black box. So because you put the data, you train it, that model is able to learn and to do some prediction or pattern recognition. But we don't know what's inside, really, right? Because it's not like y equals x plus b, that's a formula. So everybody understood. Okay? If you say, what's the relationship, that's the formula, everybody understood. This one, there's no formula. So you don't really know what's inside. That's why you call it a black box. So sometimes people commented on that. Another one is that it may not be portable. So the data that you use to train for, let's say for Hong Kong, right, probably doesn't work in Macau or doesn't work in Shenzhen, right? So that model that you train may not work. So that's kind of a disadvantage for neural network. Right? It's not portable. It's a black box. Whereas the advantages would be that it's really good at coming up with a non-linear relationship. Okay. I'll explain a little bit more in detail about I'm going back a few slides and I come back in. So in the past, what happens is that you have your input, you have some rules or some functions, and then you get an answer. Okay? So this is what we do. So for example, if you want to know the answer, but you need to know the function, right? So if your input is x is 2, then you know y is 17. So there's a very straight relationship. But you need to know, before you know the answer, you need to know the function, right? So for example, you might want to convert the temperature, degree Celsius to degree Fahrenheit, right? So, but you cannot convert until you know the relationship. Celsius equals Fahrenheit equals to Celsius times 905 minus plus 32, I think, something like that. That kind of relationship you need to know. All right? Otherwise, you cannot. You cannot get the answer. So you need to know that function first. Or, for example, if we more transport related, would be that if you want to determine whether people are from the speed that you measure, whether people are walking, cycling, or running, you can make some rules. You can say, okay, if the speed is less than 5 kilometers per hour, the person is walking. Okay, this is the assumption that you make. If they are less than 20 kilometers per hour, I think they're cycling. Okay, anything more than that, that's driving. So that means that you need to know everything like that. Then you write the rules. If you get something like I don't know, maybe 10 kilometers per hour, what's that? So it could be somebody running, right? It could be somebody running too. It could be cycling. It could be running. Probably not walking, right? So again, you need to add new rules for the model to work. So this is how we do that traditionally. So now what we call the data-driven approach. People talk about big data, machine learning. So this is what it is. That you have your input, you have your answers, and you use some machine learning, and then what you get is a model. So some examples would be, okay, so maybe one example we can do is, so if we, back to the apple example. So if we put the input as the weight, the color, you know, and the shape, and then it says the answer is the apple. Okay, so the different shape, different weight, different color, maybe different sugar content, and then that's the apple. So you have all the apples that we saw. We take all these measurements. So these are the input, and we tell them that this is an apple. And then plus we took those the oranges once. It says, okay, well, if it's round and it's orange color and it's this weight, and that's an orange. So that's how we haven't told. There's no rule yet. So you just give the parameter and telling what it is. Okay, so this is what we call supervised learning. So you have your input and then your answers. Then you put the machine learning. What comes out is actually a model. Okay, so that model actually will understand through this learning. It would know given input, that's the answer that you expect. So from this model here, what you get after you have trained it, what you do is that you provide a new input, you run it through this model, and it will give you an answer. Okay, so that's quite different from in the past where you need to build this yourself. So what with the data-driven part is that you don't need to have the model. You use machine learning to train the model that way. Okay? So the paradigm is very different. Okay? The paradigm is very different from the past. Okay, so I'm going to go through the next bit, and then we can take a break. So in terms of neural network, you have seen the input layer, the hidden layer, the output. We have weights for all these connections. Okay, so this is the typical setup for a neural network. So let's suppose you have time series data. We want to predict travel time. So we have 8 o'clock, it's 14 minutes, 8:05, 15 minutes, 17, and so forth. Okay, this is the time series. So what we want is a prediction. So we want to predict the next step, next time interval, what that time interval would be. So in the input and output data, I would prepare something like this. So if I see 14, 15, 17, next one I should get 18. So basically 14, 15, 17, next one I want to predict 18. Okay, so next one I said 15, 17, 18, I want to predict 20. Right? 17, 18, 20, 21, so like that. Okay? So this is given these three input, I want them to learn that the next input, the output is going to be this. Right? So that's the next time interval travel time. With me? So this is the time series I get. This is related to question number 3 of your assignment number 1. Okay? Similar ideas. So this is the input you have. This is the data that have your time series. So you could, one of the ways could be that you provide the past 3 input and give 1 output. Okay? So 3 inputs, 1 output that way. So what happens is that you have these 3 input here, and you tell them what this output is going to be. Right? So when you do that, initially the model would have different random weights assigned, and you put this and tell them is that. And it could be that they start to predict, okay, given this, the answer is 21 because of the initial weights. And obviously 21 there's an error, it's not correct, right? So the model will go back and fix some of the weights to make it closer to 18. Okay, so through one training. And then you provide the second input, and then they make a prediction. Again, there is some error, so it keeps adjusting. Every time you give a new data set, it starts to adjust the weights. Okay? Until you provide thousands of time of training data sets, until the weights get adjusted, and then you can predict quite accurately. Okay? So this is basically how a neural network works. All right? So you have input, your output, they train the data, there's some errors, they fix the weights. Okay? And then and then you put another data point, the train, a bit of errors, you fix the weight. So they keep adjusting that way. So after you have trained the model, then you put a totally new data set and you test to see whether you've given some inputs, whether the output is what you expected. Okay, so to see how accurate the model is, whether it's accurate enough for your work. I've talked about this before. Okay. So basically, this chart is to say that okay, after you've done the predictions, you can then provide the information to people. Okay, I think this is a very last. So when we want to do travel time predictions, sometimes we want to predict. There's some challenges, right? So if you want to predict what might, if I leave here at 10 o'clock or 11 o'clock, what will be my travel time? Versus if I leave here at 9:30, what will be my travel time? So do you think the accuracy to predict what I will leave at 9:30 the same as what if I leave at 11 o'clock? Do you think the accuracy will be the same in terms of the travel time predicted? So one is I'm leaving in less than 10 minutes from now. Another one, I'm leaving an hour and a half from now. Do you think it's easier to predict? Do you think the accuracy is the same? Do you think one is... No, why not?
Maybe 10 minutes is easier way to predict because it's very close to us.
So let's suppose if it's 1.5 hour time, what would you do? Because you talk about, and I totally agree with you, that it's very hard to predict 1.5 hours time. What would your solution be if I ask you, okay, what do you think my travel time would be at 11 o'clock? What's the method that you would use?
Use my experience as a method.
Okay, so basically, you just use a historical data, right? So what you said, you find that even currently, I think about 45 minutes to an hour after that, the prediction is actually, the accuracy is very low. So it is as good as you use the historical data because there are too many variables, right? Too many uncertainty you do not know. So the historical data average of in the past, I know that this is roughly that prediction. The accuracy is just as good as any techniques because there are too many unknowns. But in the shorter interval, those techniques are quite good, right? Because you have all the inputs, all the histories, you can match the pattern. But an hour and a half, not very good. So there's travel, like the travel incident and so forth. So this is just saying that, if you are around here, you don't know what's going to happen, later. So I think we talk about this a bit, like, are Google and other travel time information truly real time? And is travel time provided to you what you experience? I think these are, how accurate is the travel time information? So these were really the gist of this class is that, people say, okay, this is real time. This is real time information. What does it actually mean? I think you should start to think about that. Right? Is it what you experience and how accurate it is? Okay. 5 minutes overtime. So we take a break and then we come back and do